All right, second example. Here is our flow system. The thickness of the slab is 3 inches. And the BW here is 15 inch. The center to the center of the beam, we have it as 6 feet. And we have the D as 24 inches. All right. The first step, just like what we did before, is trying to find what is the effective flange width. Those are three equations. 1/4 uppercase Ln equals smaller than BW plus 16 HF smaller equal to BW plus lowercase ln. And the first one, 1/4 times 18 feet, that is the length of the beam. I'm going to change that to inch, and that is going to be 54 inch. The second one is your 15 inch plus 16 times the thickness of the slab is 3 inch. That will give you 63 inch. The third equation, that is 15 plus 6 feet. That is the center to centers. We need to subtract 15 inch divided by 2, half for each side. That will give you 72 inch. Right? If you look at all those three, the first one is governing. Therefore, your BE is equal to 54 inch. Right? Everyone good so far? With that, now we can find the level arms. Before we do that, we first find out what is the moment that we need to take care of. 1.2 dead load plus 1.6 live load. The second equation is 1.4 dead load. If you put those numbers in, 200 kfeet plus 1.6 times 425 kfeet, that will give you 920 kfeet for the first equation. The second equation, 1.4 times 200, that will give you 280 kfeet. And the first one is governing. We assume your feet is equal to 0.9, therefore Mn is equal to Mu divided by phi, that is 920 kfeet, divided by 0.9, that is 1022 kfeet, that's 1022 kfeet, that is the moment that your beam has to take. Okay? We can assume our moment arms as what we did before, as the maximums of 0.9 D and H minus HF divided by 2. If you put those numbers in, that is maximums of 0.9 times 24 inch and 24 minus 3 inch divided by 2. The maximums of those two, the maximum of 21.6 inch and 22.5. Therefore, your Z is 22.5 inch as the starting point. And with this, your AS is equal to Mn divided by Fy times Z, that is 1022 kfeet times 12 inch per foot divided by 60 ksi times 22.5 inch, that is 9.08 inch squared. Right? Everything is the same as before, right? It's very similar to the first example, just different numbers. The third step, find the neutral axis location. What we have done before is we calculate the AC is equal to AS Fy divided by 0.85 F prime C. We put those numbers in there. That is 60 KSI times 9.08 inch square divided by 0.85. F prime C is 3 KSI. That will give you 213.6 inches squared. All right. And based on our BE, this is our cross section of the beam. We have the thickness of the slab as 3 inches. The BE, we calculate that as 54 inches. Your BW is 15 inches. So now we require the AC as 213.6 inches squared. Is our Whitney stress block located within the flange or the web? The web. Why is the web? Exactly. So the flange area AF is equal to 54 inch times 3. That is 162 inches squared, which is larger than, which is smaller than AC. Therefore, the stress block need to be extended into the web. How much it extended to? The depth that extended can be calculated as your AC minus AF divided by BW, and that is 213.6 inch minus 162 inch divided by BW is 15 inch. That is 3.44 inch. Right, now this is our new cross section here. I'm going to enlarge a little bit to make it clear. Your BE is 54 inch. HF is equal to 3 inch. Now this Whitney stress block need to extend it to 3.44 inch down. This is 3.44 inch. And this is our reinforcement. The BW here is 15 inch. And we know that our D is equal to 24 inch. All right? We first need to figure out what is a centroid for this T-beam. That is the location where your compressive force is acting at, right? Once we calculate the centroid, then when the D is known, we know that what's the level of. We do not need to do that for the previous case because previous case, the neutral axis is located in the flange. Therefore, we're designing as a rectangular beam. But this is a true T-beams. Therefore, we first need to find out what is the Y bars. I'm going to use my reference X as the top of the T-beams going downward as my Y. Therefore, my Y bar is going to be sigma summation of AI yi divided by the summation of AI. I'm going to use the top as my area 1. So this blue shady area as my area 1, and this green shady area is my area 2. All right? that is A1 Y1 plus A2 Y2 divided by A1 plus A2. You have done this thousands of times. I'm sure you can do this centroid calculation. For A1, which is 54 times 3 inches, your Y1 is half of the distance, so 3 inches divided by 2. A2 is your 3.44 inch times your BW is 15 inch times the distance between the centroid to the top of the section, that is 3 plus 3.44 divided by 2. Oops. 3.44 divided by 2. All right, divided by 54 times 3 plus 3.44 times 15. That will give you your y bar as 2.28, meaning the centroid of this cross sections of these T-beams is located in somewhere here. That is your centroid. All right, once the centroid is calculated, now you know where's the moment arms. The moment arm is this distance here. This is your level arm. And your Z can be calculated as T minus your Y bar, that is 24 inch minus 2.28 inch, that is 21.72 inch. All right, and the assumption we have, the level arm is 22.5. Now, the first iteration, your level arm is 21.72. With this, we can use iterations to refine the Z and the AS. Right, your AS, the first iteration, your AS is MN divided by Fy times Z, that is 1022 cubic feet times 12 inch per foot divided by 60 KSI times 21.72 inch, and that is 9.41 inches squared. That is the required area for steel, and you can calculate your AC as Fy divided by 0.85 F prime C. If you substitute the numbers, 1 inch squared divided by 0.85, F prime C is 3 KSI. Now your AC is 221.4 inches squared. That's still within your flange, right? Because your total of the flange is 162. Oh, you're still within the web, my bad, right? And the depth that need to be extended is equal to AC minus AF divided by BW. You put those numbers in, minus 162 inches squared divided by BW is 15. Now that becomes 3.96 inch. Then you need to recalculate your centroid because your centroid has changed, right? Once your T-beam, once your the T section is changed, the centroid changed with it. Now you can calculate your Y bars again. That is 54 inch times 3 inch times 3 inch divided by 2 plus 15 inch times 3.96 inch times 3 inch plus 3.96 inch divided by 2 divided by 221.4 inches squared. That will give you your Y bar, new Y bar as 2.43 inch. And your new moment arm is equal to D minus Y bar that is 24 inch minus 2.43 inch, that is 21.57 inch. Right? It's still different than what we have, which is 21.572 inch before. And now you can do one, continue doing the iteration. Now we could do your B, C, D, E, right? And after all this iteration, now we can find out my AS is equal to 9.51 inches squared, and the depth extended is equal to 4.12, and that this is the same as previous iteration. Then we can stop. Right, and that's finally converged. But that has go through, I have went through 5 different iterations to get to this point. Right, it's take a long time. That's why we have another method that is quickly get to this point. So this is just showing you a way to do it, but it's probably not a good way to do it by hand. But in the computer programs, actually using the same method you do this, because computer can just iterate until it gets close, right? So that's that. Once that's done, now we do the same things. The fifth step is track AS mean. Your AS mean has to be larger or equal to 3 times square root of f prime c, fy, bwd, 200, fy, bwd. Put those numbers in. That is 0.99 inches squared. This is 1.2 inches squared. The second one is governing. Your AS is equal to 9.51 inches squared, which is larger than AS mean. Therefore, we okay. Just to complete this example, the sixth step is to track the assumption that we make. Your A is equal to 3 inch plus 4.12 inch. That is 7.12 inch. Your C is A divided by beta 1. That is 7.12 inch divided by 0.85. That is 8.38 inch. You can calculate the strain at the steel location using this equation. And that is 0.0056, which is larger than 0.005. Therefore, is a tension control section. Therefore, your phi is equal to 0.9. Therefore, AS required is equal to 5.91 inches squared. Right? That is done. And yes.
We get a question where we in the final like this, we don't actually have to use this method. We can use the next method.
Right. So if in the final, if you see this, I highly recommend you not to use this method.
So we will never have to be forced to use this method, right? Like this will never be the only option to use.
Right. It's never going to be the only option to use. The reason that we go through this example first is showing you, how the computer program is actually doing. So if later on, if you try to develop your own spreadsheet, if anything happens, if anything goes wrong, then you know where to find it, where to find the error, right? And the second method that we're going to use, that is dividing your T section into the web and the flange, right? Computer don't know how to do it. So that method is very hard to put in the computer. That's why we need to go through this method so that in your project, in the final project, you know how to program it. Okay? And with that said, we're going to talk about the another quicker or simpler method next class. Any questions? If none, let me first